Hey, hi everybody. This is the 121 review session. I just want to start out. What do you guys think you are having trouble with? Maybe there's some things I could focus on. Otherwise, I was just going to go through a midterm, and I also have some other sample problems. I think predicate logic is going to be tough for a lot of people because I know it was tough for me. It still is tough. And also circuitry, I think I had a hard time with. So maybe you can focus on some circuitry. Great, good to hear. Oh, I see. Okay, I'm going to share my screen and start going over some things then. Which one? Okay, so why don't we start off with some predicate logic. You guys can write down, I think we'll just take a couple minutes for each one. You guys can write down your answers, or you can just do it in your head. Some of these are pretty simple. Some of them can get more difficult. So why don't we take like 1 minute each, and then we'll go over them. So start with this guy here, 2A. All right, this one was pretty straightforward. There's two ways you can go about this. First, you can declare there is an animal that is green, or you can say there is no animal. For all animals, there isn't a single one, and then nullify that entire thing. So it is not the case that for all animals, there are no green animals, if that makes sense. Actually, I gotta figure out how to type these out. Maybe I'll get a whiteboard. Actually, yeah, that's a better idea. I'll put the thing I'm reviewing in the chat, and then I'll get a whiteboard out and try to write these ones down. Oh my God, just go. Where's this? Sorry guys, I'm a boomer. Okay, there we go. Okay, so why are you doing this? Okay, there we go. So with the first case, there exists, what is it, X? Yeah, so if X is in the set of animals, so if X is in A, then that's a comma. Then there's a green animal. Conversely, you can say it is not the case that for all animals in A, there are no green animals. And you can see just by if you carry this over, so you turn this into a not, then carry this over here, and then just get rid of that. They turn out to be the same thing. Clear. There's got to be a better way. Okay, for the second one, no dogs are green. So that there's two things that you have to consider here. One, that that you have to consider the fact that that you only have the set of animals, you don't have the set of dogs. So when you declare for all for all x in A in the set of animals, first off, if x is a dog, then we're going to say green. So this is saying for every dog in the set of animals, or sorry, for all animals in the set of animals, if x is a dog, then it is not green. And conversely, we can also say that we can prove the opposite. We can say that there exists an animal in A, and that animal is a dog, and that animal's green. Personally, I like doing the reciprocal cases. I think it makes sense to do it that way, but you guys can do it whichever way you want. Does this make sense? I'm gonna take silence for a yes, I guess. I don't know if I can fit the chat on here.
I had a quick question.
Yeah.
What if we were to own, because when I wrote it down, I just had for some x in the set of animals, and then I just negated the and. So what does that say? What am I saying there then?
So you're negating the entire and.
Yes, I just negated.
Yeah, that'll work too. Because if we bring this over,
Yeah.
then that's negating this entire thing, and that's changing this guy to a for all. So yeah, that works too.
Okay, perfect.
Okay, so there is a non-dog that is larger than a dog. Okay, this is where it starts to get interesting. So we do have two variables here. So the variable that we're going to consider right now is x. So we're going to say, because we're saying there is a non-dog, so there is a non-dog. And now, if that is true, we can say that there is there is another animal that is a dog. And so if y is a dog, and then let's just say LT because I don't want to write larger than. What's the order? X is larger than Y. Yes, so X, Y, and bracket. So let's go over this. There is an animal in A that is not a dog. So we proved that X is not a dog. Now we're saying that there is an animal Y in A, and that animal is a dog, and X is larger than Y. So that's proved it properly.
Sorry, could you explain what the arrow means in this case?
Well, arrow is if, then, right?
Hi. Sorry. Sometimes I'm just like confused with when to use the arrow or the and. Like, yeah.
Yes, it can be very confusing sometimes. And to be honest, sometimes it's really up to it's really up to the nuances of the English language. In this case, you have to declare the fact that X is not a dog first, and then if that is true, because if X is not a dog, then this whole thing is invalid. So we're saying that X is not a dog, and then we're going to go to this secondary statement here. It should work to do it in the other direction too. If Y, so you could replace this with Y and dog, and then X not dog, and LT XY. That should produce the same results.
Sorry. Could you explain again why do you have to declare there's a animal that is non-dog again? Like you said if you don't declare that, then you said the whole thing is not even true. Is that sorry, what did you say?
Well, if you don't, so I think you guys are talking about putting all these in an and statement, right?
I mean, I think the thing that I don't understand is why do we use if then? Like, yeah, if then is the thing that I don't quite understand. Like, basically the arrow in the middle. Because you say, yeah, we represent if then, right? But yeah, I don't really understand.
No. Yeah, so you guys are talking about, it's like if, I'm just going to do this a bit shorthand. Okay, there exists an X, there exists a Y, D, not D, X, and D, Y, and LT, X, Y. Is that what you're saying? Because if you don't have a if you don't have an if then that's is probably the only.
Oh, okay.
Well, not dx and dy. X doesn't equal, well, you don't have to declare X doesn't equal Y because X is a dog and X is not a dog and D and Y is a dog. So in this case, you don't have to declare X does not equal Y because it's implied.
So the way you do it, I mean, the way you write it here, I mean, the very last line that you say that exists X, comma, that exists Y, this is also okay answer, right? This is also correct, right?
No, I'm saying this. Well, let's go through it. Let's try to find a case that disproves it. There's a non-dog that is larger than a dog. So we do just have to find one single case, don't we? Yeah, the if thens can get confusing before you translate into an and. So why don't we translate this to, one sec. So what? Can you guys remind me what's a I don't have your guys' note sheets in front of me. What does the if then translate to? Is it it's not, if P goes to Q, then it's
It means not P or Q.
Not P or Q. Yeah. Okay. Thanks. Okay. So this is a case where it's one of those weird like single cases, because an if then statement is true for 3, and an and statement is only true for 2. Sorry, 1. So yeah. So if you reverse it properly, then you can turn it into an and statement. You just have to make sure that it's the proper case, because. So, 0, 0, 1, 1. oh, sorry. God, this is so frustrating to do on a blackboard. If you guys were in a classroom, this would be going much smoother. Okay, this is and this is if then, right? So you can see the difference between these two. So you could actually turn this into the proper case, because if you took the reciprocal of this, then you get 0, 1, 0, 0. So these could be equivalent. So this is not P or Q, and this is P and Q, and this is not P or Q, which turns out to be P and not Q. So if you make sure that the truth tables are equivalent, then you can use an and. You just have to make sure that you're doing it correctly. So in this case, you're doing not P to Q, and then we're sticking with not P and, sorry, not P implies Q, and they're sticking to not P and Q. So let me write this. Let's see, should that work? So if this is a statement, then if you want to get down to here, then you would need to be writing not P and Q. So which would turn into 0, 0. Wait. Sorry, to turn your and statement P and Q into this is not P and Q, which is the same thing as the reciprocal of the if then. So that should be P and not Q. So I think I'm just going a bit long-winded and trying to explain this a bit too hard. So yeah, this should be able to work. I think this makes a bit more sense because it's just using an if then statement, because you're declaring that this is not a dog first, and then you're going to prove the second statement. This can get tricky because if you're just stringing a bunch of ands together, you could come up with a corner case where it doesn't work. So if one thing is wrong, then it disproves it for everything. But this is going to be right. Another way of writing this. Go ahead. Another way of writing this would be no. So it is not the case that a non-dog it is not the case that, oops, sorry, that should be, let's just add in a for all there. It is not the case that for all x in A, if it's non-dog, then for all y in A, there is a dog. That implies that it's not larger than. So this is the same statement as before. So let's see how this translates to. So we're saying every x in A that is not a dog every y in A that is a dog, it is not the case that there's x larger than y, that the non-dog is larger than the dog, and then we nullify that entire statement. So this is the same thing as saying there exists a dog in y, because we can if we want to bring this guy over, and then you eventually get the same result, which is bring that over, and then some and then if you nullify this guy. Oh, God, I wish this was word. What's that? Does this statement make sense? The reciprocal? Okay, I think we're spending a bit too much time on this one. Let's move on. Do you guys want to work on a proof? How do you feel about proofs? So do you guys all have the? I'm not sure if more people join in. Do you guys all have the link I sent you? Say no, otherwise stay silent, I guess. So for this first one, 2a, is it true that if a and b are real numbers, a does not equal 0, then there is a unique real number r such that ar plus b equals 0? Ah, right, chat. Okay, thanks for linking it. Okay, so what kind of proof do you think we can do here? Let's list our proofs. Let's go through them. List by, what's the word? Proof by induction. No, that's not going to work because we don't have a recurrence relation. Proof by contradiction. I think proof by contradictions can always work, but you don't necessarily have to always use them. Actually, you guys tell me. Oh, you haven't covered proofs yet. Okay, that makes this easier because then we can go through this. So I tried to look on your guys' course website to find out what kind of content was going to be on, but it didn't say. It must be on Piazza or the lecture notes, which I do not have access to. Okay, have you guys covered DFAs? DFAs, what have you guys covered? You haven't covered proofs, haven't covered DFAs. Okay, well that's good because DFAs are gross. How deep into circuitry have you guys gone? Which is at the end of predicate logic. How deep into circuitry have you guys gone? Okay, so why don't I pull up this mux question and see if you guys can do this. Which practice midterm are you guys talking about? Oh, this review sheet. Okay. Okay, so why don't you take a couple minutes to go through this guy. Flip-flop is, have you guys done covered flip-flops in the lab? Okay, flip-flops is sort of what it sounds. It's going to be like an alternating circuit. So the part B, they're asking something that's counting even numbers, which is basically just implementing a circuit that just counts from 1 to whatever, except there's a flip-flop involved. So it's only going to alternate between turning it on and off. And so it's going to be off for 1, and then on for 2, and then off for 3, on for 4, and that way it's going to count even numbers. Yeah, if you guys have practice problems that you'd rather go over, then by all means. I was just doing my best to try to find some good stuff online. I found one that's really helpful for just figuring out what multiplexers are. Yeah, like I'm not super confident that flip-flops, like complicated stuff about flip-flops, would be even on the midterm. I know in the past they haven't. Like you've definitely had multiplexers. I think it'd be probably more useful to focus on stuff like that. If you want, we can skip the flip-flops and go straight to like multiplexers and stuff. Yeah, so I mean, I can't really speak for your professor, but if it was just on this week's lab, I'm probably wouldn't be covered, I would imagine. I would hope. Here, let's skip flip-flop for now. Okay. You guys gave me that question. I haven't seen it yet, so I'll take a look over it. Why don't we go through this one? I think this is really valuable, just to do some stuff about multiplexers. So basically, we're just filling out what the values of each one is going to be. It was well, let's focus on the basics first. Then maybe if we get to the end, we can do flip-flops. So remember with the multiplexer, so the function is going to be governing which gate is open. So if it's 0, 0, so this one, 0, 0, 1, 1, 0, and then 1, 1. Okay, that's good. Okay, so no flip-flops. Forget about flip-flops. Let's stick to multiplexers. So I think value, like I think these first four are going to be pretty simple. The last one might be a little complicated, but I can explain that. So why don't we take a couple minutes? This would be good value to go through, like even just like addition and subtraction of binary as well. So when we take a couple minutes and try to go through the first few ones of these, actually I'll do them too. Okay, why don't we go over the first one? So you can see the multiplexer, the function is 0, 1. So that means that this is 0, 0, this is 0, 1. So this is going to be, if you follow it, that's b minus a. So b minus a is going to be the same thing as b plus 2's complement of a. So b equals 0, 0, 0, 0, 1, 0, 1, 1. 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0. Does everybody see how I got the answer there? It's just adding these two numbers together. And let's forget about value 0 for now. So number 2, the function is 1, 1, so that's XOR gate. So XOR A XOR B is going to end up with 0, 0, 1, 0, 0, 1, 0, 0. How do you know what each function combination does? What do you mean by function combination?
I guess like in the middle, you have function. So you have 0, 1, 1, 1, 0, 0, 0, 1. And you just, when you went through that last one, you're like, we know it's subtraction because it's 0, 1. And I was just curious how you got to that.
Okay, well, if you remember from multiplexers, the bottom gate is what controls which gate opens it. So basically a multiplexer just allows one of 4 or 8, 16, whatever. In this case it's 4. It allows one of the gates to travel through. So in this case, the function is 0, 1. So the top gate just goes through binary. So it's 1, 2, 3, 4, or 0, 1, 2, 3. So this is, the top one is 0, 0. The second one is 0, 1. Third one is 1, 0. And the fourth one is 1, 1. So if the function is 0, 1, we go to the second one, and then we trace that back, and that traces back to the subtraction. So then, because the output of the mux is value e, we know that in this case, for function 0, 1, value e is going to equal b minus a. Does that make sense?
Yeah, thank you.
And so for question 2, we can do the same thing. The function is 1, 1, so it's going to be the bottom gate. 0, 0, 0, 1, 1, 0, 1, 1. We go back, it's an XOR gate. XOR gate's pretty simple. We XOR the two numbers and we get 0, 0, 1, 0, 0, 1, 0, 0. And in this case, because the function is tied to both multiplexers, the function is 1, 1, so we are looking at the bottom gate for value 0. So in this case, we know that value 0 is also 0. I didn't cover it for these two because I think it's a bit more complicated, and you guys don't necessarily need to know this for the midterm. This is a bit of an obscure case. Yeah, Khalid, you can just talk if you want to. You don't have to raise your hand.
Oh, thank you. I just want to know, are we assuming that they're all signed, pretty much?
Well, it doesn't really matter, does it?
Yeah, I guess you took the complement of A.
Well, that's how you do. It doesn't matter if it's signed or not. It only matters for when it's signed. It only matters when you're interpreting it into a decimal number. So if it begins with a 1, then it's going to be a negative number. But it's still the same. It's the same number in binary, and we're just asking for what the number in binary is. So you don't necessarily need to know if it's signed or unsigned. If that makes sense.
Oh no, but right, but you also need to flip it to then add them together, right?
Yeah.
Okay.
Well, that's just how you do subtraction. So I flip the bits of A, added 1, and then combine the two numbers together.
Okay. Okay, got it.
So for this one,
sorry. I'm a little bit confused with the C in and C out, B in and B out, like how we flip it. I kind of forgot.
Sorry, what do you mean how you flip it?
Like how do we reach to the bottom mux instead of the top one?
Like what function controls the output?
No, the how we like reach to the multiplexer there, where you're pointing at instead of the top one. I kind of
Well, if you just follow the
forgot.
wire, I mean, this just goes straight into the multiplexer. But this top multiplexer is
No.
only controlled by the bottom. So the if you look at the documentation on the gates, the right one is the output, and the bottom one isn't the output. It's something different. I'm not really, I'll go over it at the end. But the output of the gates is going to be what's coming off on the right. So these four gates, all the output of these four gates are going into this multiplexer, and then it's controlled by the function. It's XOR, not OR, I think is the, wait. What did I say XOR was? I think I wrote down what. Sorry guys, I wrote down the wrong numbers. Or wait, no. So 0, 0 and 1 is going to make 0. 1 and 0 is going to make 0. 0 and 0 is going to make 1. 1 and 0 is going to make 0. 0 and 1 is going to make 0. 0 and 0 is going to make 1. 1 and 0 makes 0. 0 and 1 makes 0. I think you guys are talking about, you're thinking of an OR gate. So OR is 1, 1, 0, 1, 1, 0, 1, 1. XOR is 0, 0, 1, 0, 0, 1, 0, 0. Do you guys know the difference? So remember that an OR gate is what you're talking about. You're taking either of the two. If either of them are 1, then you're returning a 1. But an XOR returns 1 if both of them are 0 or both of them are 1. If they're different, it returns a 0. Nope. No, XOR returns true if both of them are the same. So for XOR, if 0 and 0, that equals 1. If 1 and 1, that equals 1. If 0, 1, that equals 0. If 1, 0, that equals 0. No, 1 XOR 1 is 1. If they're the same, it returns true. Let me double check, because you're making me question myself, but I'm 99% confident. Let me bring up a truth table.
XOR if they're both true or both false. I think it's false.
I think you're thinking of an XNOR.
Yes. Sorry, you're right. I had that backwards. But that also means where did we go? Wow. Yeah, I'm sorry. I'm sorry. I got the answer completely backwards. I got my XOR mixed up. 1, 1, 0, 1, 1, 0, 1, 1. Basically the complete inverse that I had. Sorry, my mistake. I haven't taken 121 in 2 years. I'm a little rusty. So yeah, sorry. An XOR returns 1 if either of them are 1, but it returns 0 if both of them are 1. What is that C in and C out and B in and B out? That's Well, for addition, it's the same because you're just adding them together. But for a subtraction gate, you need to specify which one is subtracting with the other one. So the fact that it's called B in and B out, it's kind of tough to say exactly what the B in and B out are referring to. I think that's just the nomenclature. I wouldn't worry about it. But the important part for a subtraction gate is the top one is going to be subtracting the second one. Yeah. So this one, yeah, C in plus C out. This one is B in minus B out. Although yeah, the nomenclature is a little odd. Okay, third one, this one should be pretty straightforward. I think you can just get it by looking at it. So what operation do you have to do for these two guys to produce this? Right, and because you can see that the only common one is right here. You can double check it if you want by doing addition to subtraction, but it's definitely the case that that's for and. So the answer here would be 0. Sorry, so the function here would be 1, 0. So this guy, you're going to be adding the two of them together. So you can do some simple addition. So it's going to be 1, 0, 0, 1, 1, 1, 1, 1. No, I can't do this in my head. One, 0, 1, 1. Okay. So you got 1, 2, 3, 4, 5, 6, 7. How are you combining ALU A and ALU B with the XOR gates? So I had that wrong before. XOR returns true if only one returns false if both are 0 or both are 1. I'll go over value 0 at the beginning, at the end. So this is just simple addition. Addition definitely gonna be on this. Definitely gonna be on the midterm. Subtraction as well, most likely. You can get some nice free marks doing 2's complement and stuff if you've practiced at it. Would highly recommend doing some addition and subtraction if you haven't already, and making sure you know 2's complement and what sign binary represents. So the answer to this one is just 0, 0, 0, 0, 0, 0, 1. And remember that. So in this case, we're actually overflowing. We're going past the 3 billion or 2.5 billion mark of the maximum of an integer, and we're going to be wrapping around to +1. So that extra 1 that would be in the 9th column just disappears, goes away, because this is an 8-bit integer. Lastly, so we have B, and then we have the value of E, and then we're saying it's subtraction. So instead of doing B minus A equals E, if you do the basic algebra, it's the same thing as B minus E equals A. So the answer that you get here, I've already done this one. You get 0, 0, 0, 0, 0, 1, 0. No, I'm looking at the wrong column. 0, 0, 0, 1, 0, 0, 0, 1. If you do addition on ALU A and ALU B, I can do it on here if you guys want. So you have, is it the pen? Yes. So 1, 1, 1, 0, 1, 0, 1, 1, plus 0, 0, 0, 1, 0, 1, 1, 0. So adding these two guys, this is 1, this is 0, carry the 1, 0, carry the 1, 0, carry the 1, 0, carry the 1. Guess what? We're going to 0 and carry the 1, and 0, carry the 1. But now this is 8. This is 8. This is 8-bit, right? So this one just disappears. We overflow and we wrap around. What's the first val E when it goes to negative number? What do you mean when it goes to a negative number? We don't really, in this context, we don't know if it's signed or unsigned, so we don't necessarily have the knowledge that it is a negative or a positive number. It's just in binary. Are you talking about wrapping around, Sean? Or like are you talking about this guy here? No, because these two, 1 plus 1 equals 0. Then we carry the 1. 1 plus 1 equals 0. Carry the 1, and then we just
like this. I think I got this because this is like overflow. It's pretty easy, but yep. I'm a little bit confused with the. Can you go back to the chart? And the first column of the val E, yeah. So it's supposed to be B minus A, right? So it goes, what's it called, underflow or something?
I don't know. That's a good question. Let's just say overflow, because it's just overflowing in the opposite direction. But the answer ends up being 1, 1, 1, 1, 1, 0, 0, 1.
Okay, so it's gonna be like a reverse back from the top to well, how should I state that?
Yeah, and you can kind of tell this is going to happen because ALU B is 8, it's 11, and ALU A is 16, 18. So 11 minus 18 is going to be negative 7. So just you can see that ALU B is smaller than ALU A, so it's going to wrap around.
Can I say that?
What's that?
Can I say that if I do subtraction for this, for similar problems like this, can I just like add 1 to in front of the B and then just do normal subtraction? Is that the way to go?
I'm not sure. I've never done it that way. I think the 2's complement is a really simple way of doing it personally.
Or just like you do it and then you flip it.
Yeah. Flip the bits, add 1, and then add the both of them together. I think that's a much easier and safer way of doing it.
Okay. Yeah. Thanks.
But if you figure out that you can do it that way, then by all means. But I've never tried it, so I can't comment on it. So Hoi, did you get? Are you good now? Because you saw that it should be 1 at the end. So that's 0, 0, 0, 0, 1, 0, 1, 1 minus 0, 0, 0, 1, 0, 0, 1, 0 equals that's first row value. Okay, so now we're done with all these. Now we can talk about val 0 for a quick second. So for 1, 0 and 1, 1, we can see that when the function is 1, 0 or it's 1, 1, it's just going to be 0. So value 0 is 0 in this case and 0 in this case. It's going to be 1 in a couple strange cases, which I don't think you guys need necessarily know about this, but probably won't come up. but it has to do with overflows. So when an AND or when an addition or a subtraction gate overflows, this is a one bit thing right here, and it's going to produce 0 if it hasn't overflowed and a 1 if it has overflowed. So in these two cases, we did overflow by subtraction and we overflowed by addition. So value 0 would be 1 in this case. I don't think that's going to be on the midterm, but that's the case.
Sorry, Brent, could you actually go through the overflow by subtraction by doing the same way you did it through addition?
Sure, yeah. Okay, so what do we got? So we got B equals 1, 0, 1, 1. A equals 0, 0, 0, 1, 0, 0, 1, 0. So already just by looking at these, we can see A is larger, so B minus A is going to flip, right? So because we're doing subtraction, let's take the 2's complement. And so that's going to be 1, 1, 1, 0, 1, 1, 0, 1. But we have to add 1. And so we get 1, 1, 1, 0, 1, 1, 1, 0. So negative A equals the 2's A equals 1, 1, 1, 0, 1, 1, 1, 0. Now if we add B to that, 0, 0, 0, 0, 1, 0, 1, 1. 0 plus 1 is 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 plus 1 is 1. Carry the 1. 1, 1, 1, 1. Does that make sense?
Okay, and how did you overflow in that case?
Well, because A is larger than B, we're overflowing and wrapping around. You can see that these all have zeros in the front, so this is not a large number, and what we're ending up with is a massive number. It's in the billions. So just by intuition, you can see that we have overflowed. It's the same thing with addition, because in addition you get like it's 1, 0, 0, 0, 0, 0, and 1, 0, 0, 0, 0. You add those together, you get 0, 0, dot, 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 dot. So just by intuition, you've gone from 2 large numbers into 1 small number. So with that intuition, you've overflowed. In this case, we're going from 2 small numbers to a large number. So again, we're overflowing.
Okay, and is that the only way to do it? You have to take the second number and get the 2's complement?
I have always done it this way. I think there is a way of just doing straight subtraction. I think this way is really simple, and it's I remember going through the subtraction, I just wasn't getting it. So I use 2's complement and add them together for everything I've done. So I can't really comment too much on compliment. I can't really comment too much on straight subtraction because I've never really done it. I've always done it this way.
Okay, and so the overflow would be 1.
Yeah, because we overflowed, then value 0 is 1.
Okay.
Okay, what else do we have on here? You guys sent me a link before. Let's see if I can find it. Actually, well, why don't I open it to you guys? Is there anything specific you want to go over? Oh, I see. Hey. Okay, overflowing in what context? Addition or subtraction? Oh, or just explaining it. So basically, overflowing is when you could be the main thing to remember with overflowing is you have to count your bits.
Sorry, I think just specifically the subtraction. Could you just explain the subtraction again?
Like just the theory behind it, or actually how to do it?
I mean, why is subtract? I mean, why is it in this case that when we subtract these two numbers, we have an overflow?
Okay. Well, let's talk about negative numbers. So how do you represent a negative number in the context of binary? Let's assume that it's an 8-bit signed integer. How do you know that it's a negative number?
Because you have a 1 at the very front.
Right. Okay. And by intuition, this you don't need to convert it to binary, or sorry, to decimal, but we can. So this is going to be 11. This is 16, 8, 18. So 11 minus 18 obviously is -7, right? So doing it in decimal, we can see that it's going to be a negative number. So if it's a negative number, it has to have a 1 at the beginning of it.
Yes.
So therefore, if we're doing subtraction in decimal, then we're going to have a 1, and so we've overflowed. Like we've gone from all zeros, now we're going to all ones, basically. We've wrapped all the way around. Like we were at the very bottom, and now we've wrapped around and we're back up at the top. It's the same thing with addition. Addition, if you have a number that's close to the limit, and so basically, like if you add two numbers together and it's over, if it's over the limit, then you're gonna wrap around and it's gonna be a small number again.
But, sorry, but in your case here, 11 minus 18 equal -7. There is no overflow, right? Because it's still okay, right?
Sorry, 11 minus 18, it does produce an overflow.
Oh, there's overflow here.
Well, it's I'm not sure if overflow is the right word, but we're wrapping around to basically to like the other side of an integer, because we have if we have two small numbers, and then we end up with something that has a 1 at the beginning, then we're wrapping around. So let's think about this in the context of unsigned integers. So let's convert this to binary. I don't feel like doing math in my head. 11111001. I'll convert. Oh. Ah. That's okay. This is basically a very, very large number. This is like 2.5 billion, right? If we're talking about unsigned. Okay. So we've done 11 minus 18, and we've gotten 2.5 billion. Underflow. Okay, thanks for the clarification. So yeah, we've underflowed here, which is like overflow for addition, but we've underflowed, and we've gone from two small numbers, and now we have 2.5 billion. So you can see where the issue is. Like, where did this number come from? We had 11 minus 18, now we have 2.5 billion. Does that make a bit more sense? Sorry, 2.1 billion. So likewise, if we have 2.1 billion, let's say we have the max integer value, so 1, 1, 1, 1, 1, 1, 1, 1. If we add 1, we get 0. So that doesn't make sense, right? Like we have 2.1 billion and now suddenly it's 0. Well, it's because we overflowed. We've overflowed the maximum value of the integer, and we've wrapped around back to 0. So if we're going the opposite direction, like we're doing this in the subtraction case, we're going from 0 and we're wrapping around to 2.1 billion. Does that make sense? Really quickly, let's talk about the last overflow case. So when I said overflow in signed binary, I realized I was doing a little bit of a misnomer. So signed binary is slightly different because if you have 0, 1, 1, 1, 1, 1, 1, 1, that's like 1 point, it's like basically like 1 billion. So this is signed 8-bit. So this is about 1 billion. If you add 1, this equals 1, 0, 0, 0, 0, 0, 0. Now this is negative 1 billion. So this is where signed binary overflows. It overflows at the at this mark. Does that make sense? Note I'm only talking about the decimal translation. So this is where like the decimal value it wraps around to becoming the negative value. You guys good? Ready to move on? Let's check out this question. Okay, I'm sure you've all looked at it before, but take a couple minutes and try to go over this guy. Also, I haven't taken a look at it, so I have to do the same thing. I'm a little confused by the wording of this question, to be honest. Design a circuit that accepts as input a 4-bit binary number and produces a 2-bit output that indicates the highest bit of the input number that is 1. Is the highest bit. Oh, I see. Okay. Okay, well, this is gonna be really difficult to do on a whiteboard because you have to make a truth table. I would, if you have time, I would really recommend making a truth table because then it makes it very, very obvious what the answer is going to be. So I'm going to take a couple minutes and do that. Hopefully I can show you on camera. Maybe I can stop sharing my screen and show you. Okay, I know it says don't create a long truth table. Hopefully in the exam you'll be able to get this, but I think doing the truth table can can help explain it, especially because we have more time right now. Let's call this. Okay, I'm gonna stop and share my screen and hopefully show you guys, and you can see. Hopefully, you guys can see this. I know it's a little tiny. So this is a correct truth table for what the output is. So this is saying for any value. So basically, like where the first true is. So in this case, this is in the zeros place. It's in the ones place here, and it's in the threes place. Sorry, twos place here, and then threes place all the way for this side. So what we have to determine is a circuit that'll give us this. And so in this case, you can take a look and just look and to see what's going on here. So they're saying it's B3 or B2. Oh, this is just for the first bit. Okay, I was confused. Okay. And then yeah. So if this is just for the first bit, we're just. So if this is for the first bit, we're just concerned about these ones down here, and you can see that it's just going to be. Is that the right one? Yes. It's going to be a 1 all the way down here. So if we look at the truth table, we can see that for if you look at the truth table, we can see that for all these values down here, B3 and B2 are true in all these cases underneath it, but they're false for every single one before it. So in this case, we can say if B3 or B2 is true, then return true, and this works for every single value of the first digit. The second one, let's do the second one really quickly. Does anyone know the answer to what is the representation for the true or false of this guy? X1 or X3? Okay, it's really hard doing this backwards. No. Not quite. We're just talking about the second, the second value. So for this one, it's NA, and then it's God, it's difficult. It's 0, 1, 1, 0, 0, 0, 0, and then ones all the way down here. So because of all these ones, I'm going to say that it's gonna be pretty closely linked to B3 here, and then also these two trues right here. you can see that that these two are true in this case. So let's see if we can combine those. I'm not looking at the answer, so I want to see if my intuition is right. So this is going to be B3 or not B3 and not B2 and B1. Well, that's kind of implied, isn't it? Okay, so yeah, my answer is correct, although I was overstating a bit. So the answer is B3 or not B2 and B1, because we're saying that it's B3 or, and then we don't need to have not B3 in here because it's implied, because otherwise, you know, it's going to be this case. So not B2 or and B1. So B2 is this B2 is this column. So we're saying not B2. We're saying it has to be in here. So not B2 and B1. So we're saying this these four cases it's going to return true only when it's not B2 and B1. And so you can see these two right here directly correspond to those guys. Does that make sense? So hopefully, I always wrote a truth table because I wasn't great at doing it in my head. It doesn't take a super long time if you have the time. Yeah, by all means, try to do it. But if you don't, and it is possible just to look at it and get it, but I find it takes a lot of practice. Yeah, it's they always say like you can determine the formula directly, but I never did. You know, I thought it was pretty hard, but by looking at the truth table, I thought it was a lot easier. Do you guys understand how I did that by looking at the truth table? I know it was really small. Hopefully you could blow that up a bit so you could look at it. So basically for stuff like this, it's just pattern detection. So the first case, you could see that it has the first four are 0, and then all the rest of them are 1s. So yeah, so I think breaking it down can be really helpful. So let's take a look at this first column for a second. You have the first four are 0, and then the next four are 1s, next four are 1s, next four are 1s. In fact, let's break it up. Okay, so if 4 are 0, 1 are 1, or 4 are 1, 4 are 1, 4 are 1, all the rest of these are 1s, and these 4 are 0. What does that tell you? What gate does that look like? It's an OR gate, right? Because if you combine all these into 0, combine all these into 1, combine all these into 1, combine all these into 1, it's 0, 1, 1, 1. So that's like that's basically an OR gate. So where is it an OR gate on? Well, it's an OR gate on these two. See, all these are false, so return 0. And in this case, all of these guys are, at least one of them is 1, so then we get 1. So that's how we get B3 or B2. The second case, we can split it into two halves. So this is true for all these cases, and likewise, B3 is true for all those cases. So right away we can see that we've solved half of it already. Then in this case, we just have to find a case where it's only true in these two cases. So looking at these two, I go over and I say, oh, okay, well these two are true, but I needed to only return it when those are true. So I want in these specific cases, I want these all to be true. So I have to do not B2, and all of these to be true. So I say not B3. So not B3 and not B2 and B1 yields this. And it works for all these as well because now all these are true. So that produces false when you do the not of it. But in this case, we've already established that we're doing B3 or all of these, so it's redundant to have the B3 in the AND statement. So we can just cut that out. So now it's just in these 8. So it's B2 or B1. Sorry, not B2 or and B1. I'll see if I can post a picture. That'd be a hell of a lot easier than holding this off the whole entire time. The 4th bit represented in the function, what do you mean by the 4th bit? B0? Well, in this case, it's not represented because there isn't a case where we're alternating. Like if there was 0, 1 right here, then the only time that you get 0, 1 is when is in the B0 column. But because it's 0, 0, 1, 1, 0, 0, 0, 0, and then all ones, the only time you're seeing this pattern 0, 0, 1, 1 is in this column, because it's 0, 0, 1, 1. So if you had a case where, say this was, if this was 0, the output that you're trying to get, if it was 0, 1, 0, 1, then you would be using B0. So let's try another case. There's a non-dog that's larger than a dog. I'll do it again after we go through this one. Why is everything messing up right now? Okay, so let's try this one. So the two rightmost columns. So let's try to do the same question, but for these 2 columns. So how are you going to get a function that works for both of these? So what's the first one I made easy? What's the first column? This left one here. What would it be represented by? In terms of B3, B2, B0, B1, and B0. Right, so this is just B3. That's pretty easy. So what about this one? You've got a couple different cases going on here. Let's talk about the bottom half first. So what would the bottom, yeah, right, so it would be not B3. Now the top half, you've got 2 different sections. So you've got one that's all ones, one that's 0, 1, 0, 1. So what is this one represented by? What could it be represented by? not B2, or B3. Yeah, so not B2 or not B3, because these are all false and these are all true. And this one would be B0, false, true, false, true. That just matches up perfectly. So let's try to find something that works for everything. So first off, we have B3 for the second half. Or not B3. Or oh, wait. So an answer that works, and mind you, there are multiple answers that work here. There's always multiple, like tons of different answers that you can do for these. So the answer you can get is not B3 or not B3 or not B2 and B0. That works for the right column. But then of course we can condense this because of the, I don't remember what the rule is, but we can take away one of the B3s because that's redundant. So B3, not B3, or not B2, and B0. What would also work is not B3 or B3 and B0. But of course, having not B3 or B3 is redundant, so not B3 or B0. Actually, no, that doesn't work. No, you have to have the B. You have to have the and there. Does that make sense? You guys see how I got those answers? This is just for the rightmost column. Yes? No? We good?
Brent, is this for the truth table? You just changed some stuff in the truth table, right? Or is this for the original question?
Yeah. No. I changed. I basically just added two new columns here. So it's not the original question before.
Oh, okay.
These two columns, what would it be? So for the left column, this is just B3, and the right column, it's not B3 and B2 and B0.
Okay, got
Sorry.
it. I think I have the answer for the original one, so that's why I was getting confused.
Yeah. Do you guys want to go over maybe a little bit more of a complicated one, and then we can turn it into a circuit? Which circuit question were you asking? This one, Michael? Oops. I'll just link it. I found it on UBC CSSS or whatever it's called. If you just Google comp sci 121 midterms, it's the first thing that pops up. Oh, that's the thing I just opened. Whoops. Go away. Okay, how about I create a bit more complicated one and then we can go through it together. How's that sound? It'll take a second for me to write it, but
Brent, actually, do you think you could go over the one that I posted earlier?
Can you post it again?
Yeah, it's in the chat now. Apparently, this might take time. So if you want, we can do like the 2-bit version of it.
Okay. Did you post it again? I feel like scrolling up.
Oh, sorry. I'm just doing that.
That is this question. That's this question I was just going over. Is it not? Oh, sorry. We didn't finish it, did we? You're talking about this question.
No, I'm talking about the one I just posted in the chat.
Is this from a midterm?
Yeah.
Can you just look the midterm? Unless you downloaded it. Takes in 2 3-bit unsigned numbers and returns true if and only if. Okay. Just give me 2 seconds. And it returns. Okay, so we're just returning one column. Call that output. If and only if 2 numbers are equivalent, or if the 2 numbers differ. Oh, this is a great question. This is exactly what I was looking for. Thank you. The 2 numbers are equivalent, or if the 2 numbers differ by 4 and are both even. So right away, we can. Oh, I see. Okay, I'm not going to make a truth table for this because it's going to be gigantic. Actually, yeah. So this one, the truth table would be like truly massive. I suppose you have the solutions to this one.
Hang on, I'm just looking.
This is one of the summer ones, isn't it? I remember the summer ones being way more difficult than anything we actually got.
No, I think it's a winter term one. Oh no.
Oh, yeah, summer. For some reason, the summer ones are always harder. Just the way it is. Yeah. So as I thought, the answer is very ugly. Let's take this down a notch. Let's say it takes in 2-bit unsigned numbers and returns true if and only if blah 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 blah. And then maybe we can see a pattern and figure it out from there. Oh, well, I guess the second case is never going to be true, is it? Let's say if it's differing by 2 and are both even. Because this is a really hard question, actually. It's very complicated.
Thank you for saying that.
It is like expecting you to do this in your head is completely outlandish. Like I've never been able to do these in my head. Like I have some basic ones, but when they get complicated like this, it's like, come on, man. I mean, if you look at the solutions, it's 3. Really? It's 4 XOR gates, 3 of them negated, 2 ands, and then an OR. Like how can you just figure that out? Come on. Let's do a simpler case. I'll take a picture and then we can go through it. Okay, so I wrote up the truth table. Okay, so let's try this one. Can you guys see that?
Yeah.
Okay, so let's look at this. Let's look at some patterns. Sorry, that O at the top is supposed to be output. I should have chosen something better, but that's not a 0. That's just like indicating what the column is. So you have 1 0 1 0, 0 1 0 0, 1 0 1 0, 0 0 0 1. Okay, so what kind of patterns are we looking at here? Let's actually, you know what? I'm gonna take a better picture. I'm not brave enough to open my messenger in front of you guys. Why are you sending? Oops. Who knows what my friends are sending me? Okay. So yeah, output on that side, and then I split them up into four sections, just to make it a little bit easier. So yeah, for this first section, that's obviously not B0. The second section, there's a few different things this could be. This could be not, a not implies. So this could be not B1 implies B0. This could be not B1 and B0. This could be not, yeah, you know what, that's good enough. There's a few different ones you could be, that's the simplest one. So not B1 and B0, not B0. This third one, is same thing as the first one, right? So that's, again, not B0. And this last one is B0 and B1, right? Oh, sorry, I'm mixing up my A's and B's. Oh no, that's right, B0 and B1. So okay, so now we've got our cases for each section of 4. So the first one is not B0. Second one is not B1 and B0. Third one is not B0. Fourth one is B0 and B1. Right? Yes. Okay, so now let's look at combining this a bit further. So we have two sections that are not B0, right? So how can we combine these two? What's common for A for both of these? So what's common for both of these is we have all zeros here when we have this case, and we have all zeros here when we have this case. So we can say for both of these two, we can say not A0 and not B0. Right? Or not bracket A0 or B0.
So, Brent, for the exam, depending on if we have time, we could just leave it at the solution you've got there right now and make a circuit from that, right? Without having to simplify.
Yeah, absolutely. I mean, that's what I'm doing right now.
Okay.
Because you have to figure out the cases. But yeah, like simplifying, I think is just kind of is a bit of a luxury. I'd say get your answer, and then if you want to make it prettier, by all means.
Yeah.
So yeah, like what I'm doing now is like you would like the TA would call it the ugly case, I guess.
Yeah. Because
Okay.
at this point we could just use disjunction and kind of start making the circuit for all the cases where the output is true.
Yeah. Yeah, and that's what I'm doing right now. So for the first segment and the third segment, you have the same thing, which is just not A0 and not B0. For the first one, sorry, for the second one, what are you going to have? So section 2, what's the answer going to be? So for the second segment, it's going to be not A1 and not A0 and not B1 and B0. Right? Because we want to get an output that works for like this and only in this case. So we need to say not A1, A0, and then not B1 and B0. So that ends up with that ends up for the entire thing, it ends up with all zeros except for this one, and then all zeros. Does that make sense?
Yeah.
So this last one's pretty simple. What's the answer here? So in this segment, we're imagining that all of these are zeros, and it's only true in this case. So what's that?
A1 and all of them.
Exactly, just and all of them together. Okay, I don't think I have Logisim installed, but I want you guys to take a couple minutes and see if you can make a circuit that works for this. So this would be a little bit ugly, but like there's a lot of gates, but it would work. Or you can see if you can simplify them.
Hey, Brent, rejoining. Question. Question for you, Brent.
Yep.
At some point over the last hour and a half, I saw like an ALU adder circuit up there. I think it was from midterm 2. Was the consensus that might be on the midterm?
I mean, I can't. If you guys have covered it, then there's a chance it's going to be on the midterm. You're like, I can't tell you exactly what's going to be on the midterm because I have no idea.
Okay.
There's been circuitry on every single midterm, so like there's going to be some sort of circuit. So just practicing circuits in general is always a good idea. Like you should definitely absolutely know how multiplexers work.
Yeah.
We got a really bad multiplexer question on mine. We had to implement 3 multiplexers to get it done. So that was fun.
Got it. Okay, cool.
So this is my naive solution. I know it's very messy, but that's basically just transforming the above into a circuit. So that might not get you full marks, but that would get you at least some marks. And from there, and who knows, this might actually be the most succinct solution, because we did already remove some. Like on this one, in this one we only have 2 coming in here, and there are 4 inputs, so just 2. That's already an improvement. It's possible that it might be possible to reduce this further. Like you might be able to integrate a multiplexer, but I think this would get you full marks.
Yeah, I think so. I think as long as you don't have like a full naive solution, you should be able to get full marks.
Yeah, like a more naive solution would be including B1 and A1 in this term. Yeah. Does that circuit make sense to you guys? If you can read it. Okay, great. So 750. There's the last few things you guys want me to go over. I think we'll just do like an open question and answer period. And hopefully I can answer them as best as possible. The dog question. Right. Let me see if I can pull that back up. Where did you go? So you're talking about this one, right? Okay. So there's a non-dog that is larger than a dog. So let's clear this. So first off, there exists an animal that animal is not a dog. Let's just say D, because I don't feel like writing things on this. So if that exists, then there exists an animal that is a dog. And larger than, the non-dog is larger than the dog.
Yeah, so here's my question. So what makes you use the if then symbol here?
Well, let's translate this into a different format. Okay, so if we have not P implies Q, what's another way of writing that?
POQ.
Yeah, is it, sorry, does P imply Q? Is that not P and Q? Not P or Q, or is it P or not Q?
Not P or Q.
Not P or Q. Okay, so this equals P or Q. Wait, is it?
Yeah. Yeah, that is equal.
Weird. So then what we get is this changes a bit because then we're bringing this over here. I'm sure it's not the other way around. I mean, I believe you guys. I swear it was P or not Q.
I think if it's P implies Q, it's not P or Q.
Okay, so this is equivalent.
Yeah.
So yeah, then this is the same thing as saying this. Then is not. Okay, well let's see this. So X is a dog, or so this one's going to return true if X is a dog, or Y is a dog and it's larger than. So yeah, this is one of those weird things where the truth table comes into effect. So this truth table is so if it's not D X and then dy, etc. You get so this is going to work in a couple of cases. So this is always the weird case, right? Actually, you know what? Let's just write a normal one. So P, Q, 0, 0, 1, 1, 0, 1, 0, 1. P implies Q. It's 1, 0, 1, 1. Wait. No, it is the other way. No, because for this to be true, this is the same thing as P or not Q. Right?
Sorry, your third row of your truth table is not correct. It should be 1101. Because P implies Q would say if P is true, Q must be true.
Twice. I got this backwards twice, and I proved myself with my bad proof. Sorry, you guys are. My brain is not with it today. 1101. Okay, so let's look at the two cases. So the one case, if this is true, so we're looking at this half of the truth table. So if it's not a dog, then we go into these. Then it's the two cases. So if this is false, then we return false. If this is true, then we return true, right? But for this weird case is when P is false, so D is a dog, as in not D is false, or this statement is true, and then that returns true. So if D is a dog, or this whole statement, then we return true. Because predicate logic is weird. And to be honest, it's strange. It is confusing. But this yeah, this works. So if we had an and, so basically if we had dx and dy and lt x, y, the truth table would be 0, 0, 0, 1, right? We're not taking into account when the case is when this is false, when it should be returning true, because that's what the imply statement does, even though it's strange and, to be honest, it doesn't make a whole lot of sense. It's counterintuitive, is what I'm saying.
Let me send. Yeah, go ahead.
No, that was it. What's up?
I'm sending a link to a previous midterm. It contains the solution, and let me see, on the page 5, question 7. It says 7. It's actually 8. It says that why do we almost never translate an English sentence blah blah blah, and I got really confused by the answer. So does that mean that we don't usually use the imply on the there exists?
I've never seen this. We use the implies all the time. It's really hard to wrap your head around, and to be honest, I haven't perfectly wrapped my head around it. You might be able to get a better explanation from one of your actual TAs in the course. That's very strange. But I can see where they're coming from. So we don't really care about the case when A is a dog. Like we only concerned about when A is not a dog. So they're talking about here. It would be true every time there's an element of x for px is false. So that's that's these two cases. When we're producing true, when P is false. P in this case being D of X. And yeah, that makes sense because it's not really saying very much. Like the statement is true, but it's not what we're looking for. What we're looking for, like this is what we're looking for. When it's not a dog, if it is a dog, sorry, if X is not a dog and Y is a dog, and it's greater than larger than X is larger than Y, then we're producing true. Yeah, I guess it could be argued either way, because if you get, like that question is saying, if you get rid of these two cases, then what we have is this and statement, which was just going to be, which is just this statement right here. So it's weird. Predicate logic is strange, and it can be interpreted multiple ways. If you don't want to worry about that weird case where it's true over here, then yeah, if the question says you can get rid of them, turn them into zeros, and then just make this into an and statement, I guess that's okay as well. But then you have indirect contradiction, another midterm, which says that you should be using the if thens. Which one are you supposed to believe? That's a great question.
Wait, this one says we're not supposed to use.
Yeah, and the one that I found the examples from said that you should be using it.
Oh, okay. Which year was that? I do want to take a look at that.
I'll see if I can pull up the answers.
Yeah, because I know Patrice definitely mentioned in lecture what's on screen right now. So there's like a Canvas recording of it, if like for the people that want to look at it. But I'm curious about the midterm that does show it, because that's an interesting case.
This is the problem. This is the problem with having different years, because in years I was doing it, we did this all the time. Now he's saying you should just be using and statements.
I think it's with existential quantifier, you should not use an implication.
2012. Oh, that was practice. I'm gonna stop the recording here though.
Yeah.